this is Chris Tae-young from South Korea, who is currently working as a postdoc researcher at Culicidae University, Bangkok, Thailand. Today, I would like to share a part of my Ph.D. research topic, developing chemical lures for mosquito surveillance tools. Last year, I gave a talk about high-throughput screening system for developing chemical lures in laboratory. This diffusion assay originally designed for evaluating pesticide or repellent using 3 different functions such as toxicity, contact irritancy, and special repellency. When I started my PhD 3 years ago, WHO published a guideline for efficacy testing of traps, and it recommended white tube olfactometer along with the heat assay to evaluate the attractant. However, the information about testing chemical lure candidates using the heat assay was lacking, unlikely for the white tube olfactometer. So I demonstrated additional function of the heat assay for the attractant, and it successfully published early this year. However, the laboratory test results still need to be confirmed in a larger-scale semi-field greenhouse assay to see the accuracy of the small-sized heat assay. Objective of this study is evaluate the novel chemical lures in the larger-scale semi-field greenhouse facility in Kanchanaburi province, which is located about 200 kilometers away from Bangkok and near the Thai-Myanmar border. First, we optimize the dose of each lure candidate in the semi-field greenhouse assay. And second, lures were screened by comparing the percent attraction among 6 different lure candidates using a single discriminating dose. Finally, we evaluated the synergism of the selected K lures with commercial traps. We evaluated the lactic acid-based Culicidae University KU lures from number 1 to number 6 as novel chemical lure candidates using 2 commercial traps, Biogent Sentinel BGS trap and Black Hole BH UV light trap in the semi-field greenhouse assay against diurnal species Aedes aegypti and nocturnal species Culicidae, both collected from Thailand. For the experiment number 1, we tested the field-collected Aedes aegypti and Culicidae using WHO2 bioassay, and the results show that both field populations have developed pyrethroid resistance. For the diurnal species, we conducted the semi-field greenhouse assay during daytime, while the nighttime for the nocturnal species for 12 hours each. All the 6 KU lures were tested and compared the percent attraction with 2 positive controls. One is a commercial product named diesel lure, another one is a cylinder carbon dioxide with a flow rate of 200 milliliter per minute, which is similar to the human breathing phase. In the semi-field greenhouse assay, 2 BGS traps were located 10 meters apart from each other. One side of the trap has not treated, while opposite trap has treated with the lure candidate. Each of the testing lure inserted into the trap body 10 minutes in advance. 50 non-blood fat females were released in the middle and counted the number of captured mosquitoes from each trap hourly. Total number of the mosquitoes in each trap were compared using sensitivity test to see the significance, and the data converted to the percent attraction using a formula in the picture. Of each percent attraction was compared using one-way ANOVA to figure out the best performer. In total, 8 to 12 replicates were conducted for each treatment. This is the result from the BGS traps. As I highlighted in the left box, 0.5 gram of KU lure number 1 treated BGS trap attracted significantly a greater number of female Aedes aegypti compared to the untreated trap. The KU lure number 1 shows the best percent attraction as well. Furthermore, the KU lure number 1 shows no significantly different percent attraction with carbon dioxide for the Aedes aegypti. For the nocturnal Chulex quinquefaciatus, KU lure number 6 showed the best performance, unlikely Aedes prepared KU lure number 1. Although the KU lure number 6 attracted significantly more mosquitoes, the percent attraction could not reach carbon dioxide. This result representing that the diurnal of nocturnal species showed species-specific responses against both KU lures and also the carbon dioxide. To see the lure synergy further, we tested another type of trap, namely black hole UV light trap for the diurnal mosquitoes. The protocol was similar with the BGS trap. This time, we only focused on the selected KU lure number 6 for the Chulex quinquefaciatus to see the lure efficacy with the light source. Temperature and humidity was recorded during the whole night. A table in the dark showed the results from Chulex during nighttime for the both BGS and BH traps. Interestingly, even with the UV light source, the BH trap treated with the KU lure number 6 attracted the significantly greater number of female Chulex quinquefaciatus. This phenomenon was same with the BGS trap, which has no light source. For the Aedes in the blue table below also represent that the selected KU lure treated BGS trap significantly increased the percent attraction. All these data clearly prove that the synergy effect between traps and the selected KU lures on attraction. Conclusion. In this study, we successfully demonstrated accuracy of the laboratory-sized heat assay by conducting the largest scale semi-field greenhouse assay. Both assays selected the same KU lure candidates for each species. In addition, the selected KU lure candidates significantly increased the percent attraction for both species, regardless trap types, especially for the nocturnal Chulex quinquefaciatus. However, the efficacy of the selected KU lures still need to be evaluated in field settings by comparing with a gold standard in the entomological surveillance, the human landing catch. To increase the further efficacy, it is recommended to repeat the whole process of the lure development from laboratory to field. Most importantly, the chemical lure candidates must be evaluated using the local mosquito population because each population has their own biogeographical differences. One of the reviewers pointed out the financial burden of the commercial traps need to be considered for the national vector management programs. So the cost-effective and sustainable traps are urgently necessary in the field, together with the chemical lures. This is what I prepared for today. I'd like to thank to my supervisor, Professor Thiophar, for his unlimited support with various funding sources from Thailand Research Fund, Graduate School of Culicidae University Fund, and now the postdoc program is under the Culicidae University Research and Development Institute. Briefly, my current research topic for the postdoc is developing cost-effective spatial repellent for the Thai local vector mosquito species. Special thanks goes to the late Dr. Michael Bay, who was one of my co-supervisors. He always encouraged me with his insightful comments on my PhD research. Hope that I can share the publication of this study about the semi-critical greenhouse essay within this year. Thanks for your attention, and please give me your invaluable comments on this study to my personal email address, dayun.k@ku.th.